Hello everybody. This video is brought to you by Asha Akanksha Foundation. My name is Siddharth Singh Kiryal, and in this video, I will be presenting the topic of counting inversions, which is an ADA topic. The prerequisites of this video is that you should have some basic knowledge of merge sort, some basic knowledge of arrays. You should know the basics of recursion and divide and conquer type of algorithms, as well as you should know the proof by contradiction method of reasoning. How do we actually prove things using proof by contradiction? So the topics are covered in this video are, I will first briefly go over merge sort, and then I will explain the problem of counting inversions. I will explain it completely. Then I will give a naive approach algorithm to solve that particular problem, and then we will increase the efficiency of the algorithm and create a divide and conquer type of approach for the same. I will be starting by briefly going over merge sort. So first of all, merge sort is an algorithm in which we are given an input array of numbers, in which numbers are arranged in any random order, and we have to sort the array. Now the merge sort algorithm will have two functions. One is the main driver function, and the other function is the function which actually does the sorting. So the main drivers function, in this we, like in this code, we are passing an array. This is the main array that will be considered, and it has the element stored. This is the lower index of the elements which are being sorted, which are to be sorted, and this is the upper limit of the index of the elements which are to be sorted. If the lower limit is less than upper limit, then only we have to do the sorting. Otherwise, there can be only two cases. Either L is equal to R. In that case, there is only one element, and in that case, we do not have to do any sorting. Or L is greater than R. In this case, the array is an invalid array, or the indexes are invalid indexes, and hence we do not have to do any sorting. Only in this case, we have to consider for sorting. So using this formula, we calculate the middle element. Then we follow the divide and conquer method. And we know, first of all, we know that this merge sort function will sort the array ARR from starting from the lower index to the upper index, where both of the indexes are, where both of the lower and upper indexes are inclusive in the range provided. So first of all, we will calculate the middle element using this formula. Then, as this is a divide and conquer type of algorithm, we will take the same array. We will keep the lower index same, but we will change the upper index to m. That is, we will sort the array from the lower index to m separately, and from the m plus 1th to the uppermost upper index separately. That is, we have divided the array to be sorted into two separate parts. First part is will be called the left part, and the second part will be called the right part. The left part is from the lower index to middle index, and the right part is from middle plus 1 index to the uppermost index. Now after this line, we we have got two we have got the array in which from the lower index L to M, the array will be sorted, and from the M plus 1/8 index to R index, the array will be sorted separately. Now these are two separately sorted parts of the same array. Yeah, just remember that the sorting is always being done in this ARR array. Now we just have to merge both of the parts. We are sending the same ARR array and we are sending all these three indexes. This will perform the merge function on the particular array. Yeah, just remember that you have to look at the theory of this merge sort yourself. I'm just explaining the code briefly. Now this is the merge function. These are the three things that we got. We create temporary indexes ijk. We create n1, which is m minus 1 plus m minus l plus 1. This is uh, this is the upper limit of the left half of the array, and n2 is the r minus m. This is the upper limit of the right half of the array. That is, n1 is the number of elements in the left half which is already sorted, and n2 is the number of elements in the right half which is already sorted. We to create two arrays of n1 and n2 size. Now this is the main part of the merge sort. We This is one of the main parts of the merge sort. We just go over the main ARR array and copy the elements of the left half in the L array that we created, and similarly we copy the elements of the right half in the R array that we created. Now we create three separate temporary indexes again, and this is the most important part of the merge sort. In this, we go we in we start a counter I and j from 0. Now we iterate that counter from 0 to either n1 or n2. That is, we are just considering left and right, we are traversing left and right half of the same array simultaneously. Now we are in this if condition. If the element considered in the left half is less than or equal to that in the right half, then the array will consist will hold the element of the left half, because according to the merge sort, which we are sorting in the ascending order, this element should come first. Then we will increment the left half index, which will indicate that the current element was added and now we have to add the next element. Else the li is greater than ri, and hence we have to, according to the ascending order, the right half element should be appearing in the array now. So we store that particular element in the r in the current position, and we increment the corresponding jth index. And k plus plus, k is the index for the main array, which is always being incremented because the elements are always being stored here. Now the terminating condition of this while loop is either I has exceeded become greater than equal to n1, or similar, or either j has become greater than equal to n2. Now suppose that I is less than n1, which means that j is greater than equal to n2, which means that there are certain elements in L array which are not stored in the main array, but the all the elements of the R array have been considered. Hence we will just we will just copy all the remaining elements in the main array. Otherwise we do the same for the for the R array. Now this is the overall merge sort that I had to explain. Now I will be explaining the counting inversion. What is the counting inversion problem? So first of all, in the divide and con first of all in the divide and conquer first of all in the divide and conquer type of problems, as you all know that we first of all divide the problem into several smaller problems. Then we conquer the subproblems via recursive calls. Via recursive calls means that suppose that we have generated some algorithm to solve the main problem, then we will have to use the same algorithm to solve the subproblems as well. Assuming that in the sub part that algorithm is working correctly and giving us the desired result, and then we will build upon that. Then suppose that after conquering the sub problems gives us certain output. We just combine the output, and then we solve the main problem. Now, what is counting inversion problem? Counting inversion problem. It is in this problem we are given an array. Suppose this array has name capital A and it has distinct natural numbers. Suppose this array has all the numbers, all the natural numbers which are non-repeating. All of the natural numbers are distinct. And suppose and for this lecture, I am assuming that these natural numbers are from 1 to 3 up to n. These numbers from 1 to 3 up to n can appear in the array in any random ordering. Now, what do we have to output? We have to output the number of inversions in this particular array. Now, what is the number of inversion in this array? Now, suppose A is a given array and there are numbers from 1 to 7 stored in this particular array in any random ordering. This is the indexing of the array starting from 1 and ending at 7. Suppose we consider any arbitrary two indexes I and j. Now we know that I is equal to 3 and j is equal to 5 and I is less than j. Now and we also see that ai is greater than aj. So because ai is equal to 3 and aj is equal to 1. So these type of indexes where a greater number appears earlier in the array than a smaller number, because I is less than j, this implies that the element at ith position comes before the element at the jth position. Now if the element at this ith position is greater than the element at the jth position, then we can just simply say that this will count as one inversion. Similarly, it is written here that the number of inversions in the array is equal to the number of pairs I comma j, such that I is less than j but ai is greater than aj. That is the number of all such pairs in which the greater element uh, appears first and the smaller element appears later in the array. For example, take this particular example array. These are the elements which are stored. Now, what is one inversion? Suppose this is 3 and this is 2. This is one inversion. Another inversion is 5, comma 2, and another inversion is 5, comma 4. Why? Suppose for the 3, comma 2 case, 3 has an indexing of 2 and 2 has an indexing of 4. 2 is less than 4. And we can also see that this 3 element appears before the 2 element. And we can also see that the 3 element is greater than 2 element, and hence this will count as one inversion. And in the overall, we can see that there are three inversions in the overall array, and hence now our main problem is to count and now our main problem is to count and give the total number of such inversions in any given array. And why is it so much important to count total number of inversions? Well, in the computers, this problem has a major significance, especially in the graphs and the shapes part of the softwares. This particular algorithm is used very extensively. So it is very necessary to optimize and create an efficient algorithm for the same. So how will we actually solve or go about solving this problem? The one thing that we can do is to suppose, like before entering the video, before watching the video, I would like you to have some basics knowledge of coding as well. Now, suppose how will we go about solving this particular problem? Suppose we will initialize a main counter from which will traverse the array. Suppose that counter's value at any position is I. I will draw it here. Suppose I am initializing a counter which traverses the array A, and at any position its value is small a. Now the A will traverse the array in the range 1, in the index range of 1 to 7. This is the value of A, and A will go from lower value to higher value. Now suppose we create another index B, and B traverses the array starting from A plus 1 to 7, and you can, as we are taking A plus 1, so you can take this as 6. So in this case, for each element you are suppose for each element this, you are looking at each next element, comparing it with each of the next element, and looking if that next element is smaller than given element. If that is the case, then we increment the counter indicating the number of such inversions in the array. Suppose for the suppose if the value of A is 4, then we will check it with 3. There is 3 is less than 4, hence this is one inversion. Similarly for 2, similarly for 1. Now for the case 5, 5 is greater than 4, and hence this will not count as an inversion. Similarly 6 will not count as an inversion. But 1, 2 and 3, 2 and 1, these will count as inversions. So in this particular loop, we get 3 inversions of 3, 2 and 1. So this is the thing. So what is the time complexity of the algorithm? I think it is fairly simple. It is order of n square time complexity, because there are two loops, and in the worst case, the loops will go over the entire, yeah, because of course the loops are going over the entire array almost 2 times. So the time complexity will be order of n square. Now our main goal today is to create an n log n time complexity algorithm. I have discussed the explanation part of the counting inversions. I have discussed the naive approach. Now I am going to discuss the divide and conquer algorithm. So how do we output all the inversions in n log n time? So first of all, before everything else, what might be a key idea for the divide and conquer algorithm? We are given an array, and how do we go about solving this particular problem for this particular array? How do we apply the divide and conquer? Suppose that we are given an array, and we how do we solve out? How do we go about applying divide and conquer? Suppose the size of array was n. Size of array was n. So we will divide it into two parts, two equal halves, n by 2 and n by 2. And then suppose the name of the array was A. This subpart will be considered X. This subpart will be considered Y. So we have to find, now we can divide this array into these two parts, and then we can apply the divide and conquer rule in this way. Now an inversion pair, before continuing, I will describe what is an inversion pair. I comma j. I comma j is an inversion pair. Like in this case, I said that 4 and 2s are counting as one inversion. So I will just say 4 comma 2 is an inversion pair. So where 4 and 2 are elements and not indexes, remember this. And then where can these inversion pairs appear? In the main division part. I comma j, in this case either I or j can both appear in the x part, or they can both appear in the y part, or I can appear in the x part, or y can appear and j can appear in the y part. Remember that always in the inversion pair, I is always less than I is always greater than j, but the index of corresponding to I is always less than the index corresponding to j. I and j represents the values and not the indexes. Remember this. So either they can appear in the both appear in the left half, that is x, or both they can appear in the y half or right half, that is y, or they can appear in the I can appear in x and j can appear in y. When both appear in x, then it is called as a left inversion in our divide and conquer approach. When both appear in y, it is called right inversion, and then if they appear in this way, then it is called a split inversion. Now you can suppose I create a function which suppose gives me all the number of counting inversions in this particular array. Now this function, suppose it is a black box. This function is a black box. Now we are inputting the array into this function, and it outputs and gives us the integer number of number of inversions in this particular array. Now in this black box, we are dividing the array into these two parts, and we have to find suppose the left inversions. Then we can just invoke the same black box, that is same function, on the x array, and for the right inversions we can do the same, that is invoke the function of the right array. For the split inversions we have to do something special. So this is an example provided. Left inversion is suppose x2 and x3, that is 5 and 3. Right inversion is there is no right inversion. Split inversion is 5 comma 4, that is x2 comma x5, or x2 comma yeah, because this is this is a part is y, so x2 comma y2, yeah, and those values are 5 comma 4. So the like I said that we can solve these two parts via recursion. Now for the split inversions we have to do something special. Now how efficient should that special be? How fast should that part of the algorithm be? Because right now we are at a very crucial stage in which the time complexity of this part will determine the time complexity of the entire algorithm. One mistake here and you will your time complexity of the algorithm will just peak. So we have to design an order of n time algorithm for counting these split inversions. Now our function, whichever function that you create, it will its recursion tree will somewhat look like this. This for any main problem, these are suppose sub problems, and this main problem was invoked on array of size n, and this was invoked on array of size n by 2 each. So you can say that the rate of spawning, that is a, is equal to 2. The rate of because a is equal to 2 because there are two sub problems generated, and the rate of shrinking, that is b, is equal to 2 because the size is reducing by half. Yeah, remember our assumption as both of the subproblems have equal sizes, so that's why we are able to apply the master's theorem here. Now we have to find and now we have to we apply these values in the in the formula, in the identifying formula of the master's theorem, as both a and b are 2. So this part becomes like this, and we have to find the verbs done outside the recursive calls, which is we have to find it order of n type. So the counting inversion function was high level idea should be like this. We should get an array, we should get a size, that is this size we are considering. If the size of the array is 1, then there is only one element, and in case of one element there cannot be any inversion, and hence we return 0. And then we split the array A into two parts. X contains the part A 1 2 n by 2, and Y contains the subpart of the array n by 2 plus 1 to n. Now we call recursion on the two parts. X is the number of left inversions, Y is the number of right inversions, and Z is the number of split inversions. Now what is this count split inversion function? It will yeah, just remember this. So what is this count split inversion function? It will take both of the arrays x and y, and the size and all this, and it will give us the split inversions, number of split inversions in this particular function, and then we will just return the sum of all these three numbers, and hence we will get the number of left inversions plus number of right inversions plus number of split inversions, and hence we will get the total number of inversions. Now we have to find the number of split inversions in linear time. How do we do that? Now suppose that we like remember that x and y were the two parts. So if x and y are themselves unsorted, then it is very difficult to find the number of split inversions in order of n time complexity. So we have to make x and y sorted first. So yeah, because why do we approach why do we land at the idea of making x and y sorted? Why? Because in most of the cases, in anywhere in the computer science, whenever you make things sorted, things becomes much more easier and much more workable. And in this case, as you saw that these are unsorted and there is no easy way to get the problem done. So yeah, just always try and look at the results of sorting, and perhaps you might get a better answer, because sorting always helps us do things in a much better way. That's why sorting is very important, and that's the reason for popularity of DSA course. So the like I explained the function that there is a merge sort, there is a main driver function in the merge sort, and there is another function which does the actual sorting. In that case, there is a sub part that is the main part which does the sorting, that is this part. So we just have to make some changes there to make our problem easier. So suppose now we are just using the merge sort algorithm to count the number of inversions. That is, forget everything, just use the merge sort and add just one line of code more in the merge sort, and yeah, add some return types int or anything like that here to return the appropriate values. So x and y are the sorted arrays of length n by 2. Z is the output array that we have to provide. It should be of length n, in which the x would be the left subhalf and y would be the right subhalf, and both of them would be sorted. So we initialize I and j counters from 1, and yeah, for we k initialize k traverse k from 1 to end. It is just like in merge sort, from it is just like it in merge sort to starting from here. I and j and k, all of them holds the same meaning. Yeah, just L represents x in that case, and R represents y in that case, and D represents the ARR in that case. So we just do the same thing. This is the same function. Now suppose in the merge sort at any instant you are given this state of the array. First I and is here and then j is here. I think you will get it much easily if you know the theory of merge sort. So merge sort, you will, while going through this, you will actually uh, come to know about the split inversions more clearly. It explores merge sorts. This part exposes the split inversions much more easily. So suppose at any instant the I is here and J is here, and we are comparing suppose 1 and 2. Then 1 is smaller, so 1 comes here. The I goes to 3. Similarly, 3 and 2 gets compared. 2 comes here. Then 3 and 4 gets compared. 3 adds here. Then 5 and 4 gets compared. 4 adds here. Then 5 and 6 gets compared. 5 adds here. Then 6 is remaining. 6 gets here. And it is like this. It merge sorts the array like this. And you can see that the sub halves of the array were already sorted, and we just compared, and in order of n time we just sorted the entire array. Now, to work things more clearly, I will first of all make a general claim. Suppose that the number of split inversions involving any element y in this subarray capital Y is precisely n by 2 minus I plus 1, where I is the position of the first pointer where the y is copied to D. Suppose, like in this case, you were given capital X and capital Y. Just consider this thing only. We are given capital X and capital Y. In any instance of merge sort, suppose I's value is something and J's value is also something, and the element at jth index is Y. I and J are indexes, and the element at jth index is Y. Now, in the merge sort algorithm, we are comparing the element's value. We are comparing the Y to the element stored at ith index, and suppose that Y is smaller than this particular element. Now Y is smaller than this element, which means that this element is greater than Y. Now, as X was already sorted, so the elements to the right will also be greater than this element, and this element was already greater than Y. So elements to the right will also be greater than Y, which implies that from the subarray from here on, which is indicated by this arrow, these two elements in this case, these are greater than Y, and hence whenever we find that Y is, that is element of this element of this array is smaller than element of this array, then we just use this formula to add on to the counting inversions, that is n by 2 minus I plus 1. Why this formula? What is the size of this array? This is n by 2. That is, this is the index. N by 2 is this element's index is n by 2, which is the last element of the X array. We subtract I from that and we add plus 1 to it. Yeah, for the subtraction purposes we just add plus 1, so that all the elements including this and towards the right to the end of the X's subarray gets counted. All of this in more mathematical terms is written here. uh, from x1, that is first element, to xi minus 1, that is the element to the left, all of the elements of x, that is xk, will be smaller than this element. Why they will be smaller? Because suppose if they were not small, than this yth element. That is, the elements towards the left of this particular index. Suppose they were not smaller than y. Suppose they were greater than y. Any element was greater than y. Then that particular element would have been compared with y first according to the merge sort. And as that was element was greater than y, so y should have been added to the main array. So in this case, while comparing with ith index element, the y should not get compared in this case, and hence this is a contradiction, and hence all the elements towards the left of this ith index should be smaller than y, and the remaining part I explained already. Now all of this remains the same. You just have to add a counter here. Count equal to count plus n by 2 minus I plus j. And that is just add a counter at this place. Add one single line there and you are done. How will the main recursion look like? It is, remember, this is just merge sort algorithm and there is nothing more to it. We just take the array and size of the array. We do all of this is the same. I explained it already. We take this array x as the input, and suppose the sorted array was capital B, and x is the number of left inversions, capital C is the right subarray which was sorted, B and C are sorted, B is left subarray, C is right subarray, and y is the right number of right inversions. Then we input B and C here, and then we get the D, which is the overall sorted array, and Z is the number of split inversions. We just output all of these things. This is the merge sort algorithm, and there is nothing more to it. So that's all I will be covering in this video. And in the next video, I will be talking about matrix multiplication and how to make it faster using Strasson's algorithm. I hope you understood everything in the video. Thank you very much.